Hello everyone, this is the video tutorial for lab 9. So in this lab, there are three tasks that we need to do. So first thing is we need to create a block design in Vivado using the IP integrator and configure the Zynq IP according to our needs. And the next two tasks are basically writing the simple application for the PS, right? So for the first part, we will write a hello world application and we will look how to take input from the user and how to display different kind of numbers. And in the third part, we will do this. We calculate this expression. So in the previous lab, we have done this expression using the Verilog code by instantiating the IP. So before moving forward and implementing these things, so let me motivate you a little bit. So far what we have done in ELD, we have done the hardware designing because we have written the Verilog codes that and we implemented it on the FPGA, right? So, but the board that we are using, the Zybo board, so this Zybo board is not only a FPGA board, so it contains a chip, or I should say, it contains a system on chip, which contains both part. There is a PL part and there is a PS part as well. So as you can see in this abstract view of the architecture, so the yellow part is the PL part. That is the FPGA part which we were using till now. We have not touched this part, this processing system. So there is a hardware part, which is the PL part, and then there is a general purpose processor, which we also call as the PS. This is the processing system. So it's a general purpose processor in which we can write our application, right? So as you can see, there are two ARM cores in it, and there are multiple interfaces to the PL, and there are multiple peripherals. So we are not going deep into the details of the architecture because this will be covered in the lecture and in more details. But for time being, that you must know that the Zynq SoC is uh, is an SoC which contains both the things. Like there is general purpose processor, that is the PS part. There are two ARM cores, and then there is FPGA. Right. So this is the programmable logic, and there is PS. So till now, what we have done is till now we have simply programmed this PL part of the SoC. We have only dealt with the FPGA. From now onwards, as we are moving forward to the second part of this course, that is the embedded logic design, so we are going to do the hardware software co-designing. That means we will be coding for the hardware part of it, and then we will be coding for the PS part of it. That is both hardware and software designing we will be doing. That's why we are calling it the hardware software co-design. And we will be looking into what is the advantages of it and what all the difference it creates, right? So without going further into the detail, so I will start with the first task. So this complete lab is just an introductory lab to how to design on the Zynq systems, right? So how do we do the designing, how to do the hardware designing, and how to do the software designing, and how to run the complete application, right? So that we will look into it. All right. So now let's first create a new project. So let's name it as Lab 9. Okay, so one thing that you need to do from now onwards, that you don't need to specify the sources at this time, because we will be using the IP integrator for doing the hardware design. We will not be using those writing the Verilog code that we used to do. Instead, we will use the IPs and then we will integrate them. So we don't need to specify the sources at this time, right? So we can click on next after doing this. Select the board as the Zybo Z710 because ultimately we will be running the application on that board. All right, so can click on finish. So the very first part in the design flow for this hardware software core design is to create a block design, which is also the task one of this lab. So how to create a block design, we'll look into it. So we will create a very basic block design today. We are not including the hardware part. We are not including the FPGA part. We will simply program the PS and write simple applications on it. So that simply means I only need the Zynq processing system, right? So let's see how to do that. So as you can see here, there is this thing called as IP integrator. Beneath it, you can see the create block design option. So just click on it and you can name it whatever you want. Okay. You can click on OK, and it will take a while. Okay, so now you will get this window. As you can see, this the window is called the block design. So in this thing, this is your diagram. In the diagram window, using this add option, you can add the different IPs. So till now, what we have done in the Verilog world, what we used to do is we used to instantiate the IP. So now in this diagram view, like you can simply there will be block diagrams and you can simply connect them instead of instantiating. So that is a very better approach to do. So in the add IPs, first of all, I will add the Zynq PS. That is the processing system. That is the PS part of the complete SoC. So whenever you select an IP in the block diagram, so once it gets selected, you will get the block diagram and you will always see this option run block automation. So we will always use this and we will always run the block automation. So as you can see, so there is only one IP. So it is selected PS system processing system 70. And what it will do is it is written in the description. So you can click on OK. Now, so after the automation, as you can see that we have the sync processing system here, and you can see there are multiple ports. But currently, we don't need these many ports, so we can customize and remove all these things because right now what I need is I need the DDR controller because there is a C code that I will be writing for the general purpose processor, and that C code will be stored in the DDR memory. So I need to fetch that code and execute on the system. So we need the DDR and plus fixed IO you can also select currently, right? So let's see how to customize it according to our need. So this is the complete system. That is the complete thing. As you can see, it's showing me the complete PS. So I showed you an abstract view of the architecture. This is the complete architecture of your PS section. So first of all, let's see the PSPL. In the PSPL configuration, I don't need the port this port. So they how they are doing the communication between PS and PL is taking place through the AXA protocols, and there are different ports for that. There are different kind of ports defined for all these things. This communication. So right now, as we are not communicating with the PL, I don't need these port. I can deselect them. Right. Second thing is the general can see enable clock reset. Also, I don't need the clock reset. I can also remove this thing. Rest of the things are fine in this PSPL configuration. Yeah, nothing to be done here. Now let's we'll move on to the peripheral IO pins. So as you can see, there are different kind of peripherals. Quad SPI is there, Ethernet 0, two Ethernet are there, two different USBs are there, SD cards are there. So we don't know, we don't need these things right now. We don't need USB, we don't need SD card. Though we don't need UART right now because we are not accessing it physically. We will be using the remote access to we will be using the JTAG terminal, but it's fine for currently. You can select these two, although it won't make any difference, right? So in the Mio configuration, that's fine. We don't need to do any such other changes. In the clock configuration, let's see. So do we need to do any changes in the clock configuration? Yeah, you can remove this clock because we don't. So you see, there are two different clocks. As you can see, one is the CPU clock. This is for this is given the 667 megahertz, and this is for the memory. This clock is for memory, and then there are clock for the PL. Right? You can see the different PL fabric clocks. So the clocks are different. For DDR, you can see there are different clock. For the memory, there is different clock. There is CPU for CPU. The CPU there is different clock. So you can manage the clock configurations from here, right? So I'm not going into the detail of everything because all these things will be covered in the lecture. So right now, what you need to focus on how to customize the IP using this customizer, right? Okay, so interrupts we're not using it and it's unticked. That's fine. EDR configuration, nothing to be done. So okay, you can click on OK after doing these. So as you can see, all the things are removed. Now I have the DDR, I have the fixed IO. That's what I need currently, right? So once this is completed, so till now what we have done, what we have added the Zynq PS IP, we have customized the IP, we have removed the ports which are not needed currently. Then we yeah, block automation. After adding the IP, running the block automation is kind of a mandatory thing and you should do. And after that you can customize your IP, which you have done. So three steps we have done till now. Now the next three steps are very important and needs to be done in the same order. So you have to take care of these three steps, and because they're very important. So first thing is you need to validate the design, right? So once you validate the design, you will get this pop-up. If the validation is successful, you can click on OK. The next thing is that you need to generate the output products. For that, you need to go to the sources, right click on the design, whatever is in the design sources, generate output products. So it will take a while. We can wait for a while once it gets generated. All right, so the generation of output product is complete. So this is the second step. So the first step we did was we validated the design. The second step that we generated the output products, and finally we need to create the HDL wrapper for it, right? So what this will do is it will generate the corresponding Verilog or VHDL file corresponding to the design that we have block design that we have created. So yeah, this is the third step. Create a let Vivado manage. Yeah, just uh, click on OK. So this won't take that much time. So as you can see now, the whatever the block design was, now I had the complete HTL wrapper of it, and as you can see, this is as this is instantiated as an IP. So similar thing that we used to do, whatever we used to do while instantiating. So it just created an HTML wrapper. So what you've done is you've created a Verilog code in which we are just instantiating the sync PSIP with the ports that we have defined, right? So that's what it. So by creating the block design, we are saved from this trouble that we don't need to instantiate, we don't need to write all that long code. What we need to do is we need to create a block diagram, we need to customize into the block diagram, and then Vivado will do all the things for us. Whatever the code needs to be done for it, it will automatically generate it, right? So that's all for the things that we need to do in the Vivado for this lab. So let me summarize what we have done till now again, because it is important. The steps which I am referring to, it's very important, and you to do, and you need to do the same step. So the very first thing, I added the Zynq PSIP, then I ran the block automation, then I customized my Zynq IP. Then the very essential three steps I did: validated the IP, secondly I generated the output products, and finally I created the HTML wrapper. So once I have created the HTML wrapper, now it's time to move on to the SDK part of the Xilinx. So in the SDK, we will deal with the PS, like writing the C code, how to do that. So in Vivado, we have created the hardware. So till now that you must be understanding it. All whatever we have created is the hardware. So before moving to the SDK, I think one more thing that we can do is so we can generate the bitstream. Although we have not used the PL part of it, so either you generate the bitstream or you can simply go to the SDK. It does not make any difference. So, but just to see how it is getting implemented and how there are two different parts, PS and PL. So let's generate the bitstream. So it will take uh, a lot of time than usual because there is a complete processing system that needs to be that process system hardware that needs to be generated in map. So it will take a lot of time, so just wait for that. So for this lab, although it's not mandatory, but it's better that if we can see into the synthesized design, sorry, the implemented design, and see that the PL is empty and there are components in the PS part of it. So that we'll look into it after the bitstream is generated. All right, so Bitstream is completed. Now let's see the implemented design. Okay, so this is the implemented design. So if you can see, The left part is the PS and the right part is the PL. So as you can see in the PL, there is no routing and there is no utilization of resources. Whatever the green color wires that you see that are running here, they are running only in the PS part of it, and there is nothing, no routing is there in the PL part of it, right? So this means that we have not done written anything to the PL, as we have not done anything on the PL. We have not uh, used any IP, or we have not written any Verilog code for the PL. That's why it is empty. So this is about the synthesized design that I wanted to show you, right? So we can close this now. Now the next part is we have to move to the SDK to write the C application code for the PS. So how to do that? So the first thing is we need to export the hardware. So we have generated the hardware in the Vivado. Now we need to export this hardware to Xilinx SDK, right? We need to export the, so there in order to export the hardware, just click on this. Because we have not we don't have any bitstream for the PL, so even if I don't take it, does not matter. But for the future labs in which we will be including the PL part as well, we need to include the bitstream as well, right? So for now, we don't have any such bitstream for the PL, so we are not exporting it. So just exporting whatever we have, this Zynq PS system. So this thing is done. So the final step, we need to launch the SDK, right? After exporting the hardware, need to launch the SDK. So just launch the SDK. You can export it location and workplace, select the default local to project and click on OK. So this is the software development kit. As you can see, SDK is for software development kit. So hardware we will always be developing in the Vivado, and in the, so for the software development we will be using the Xilinx SDK. By software development, it simply means writing C or C++ application for the PS part, right? So that's what it's all about. So it will take some time. So as you can see, it is initializing software repositories and whatever. All the files that are coming from the Vivado, it will use them and importing the hardware specification that we have whatever we have exported from over there, it will import all these things. Because when we exported the hardware, it created a file in the project location, and from there it read that file and it using that. So once you are done with opening the SDK, so the default window will be like this. So there is this hardware platform. So hardware platform is the hardware that we created in the Vivado, right? So this will always be there. So your hardware platform will always be there. So this is the hardware platform 0, and there will be some, this is system.hdf file which will always be opening. So as you can see, there are different peripherals and different things in the complete SoC. So in Zynq SoC, everything is memory mapped. So I'm not going into the detail of it because this will be covered in the lecture in the details. So for timing, what you can see, like everything in the Zynq is associated with some memory location, like some memory how to access anything, like any port, any peripheral, for example USB, for example SD card, everything is assigned a memory location, right? Not a single memory location, but a range of addresses, right? So as you can see, this is the base address and this is the highest address. Similarly, for this timer, for general purpose IO things, we have base address this, we have higher address this. This means that this range of addresses I have provided, or the system have provided to the GPIOs. Using these addresses, I can access the GPIO. Now, GPIO means there are buttons, there are LEDs on the port. So those are general purpose input output. So this, in order to access them, in order to display something on them, how to access them, I can use the addresses assigned to them, right? So the system.htf file is all about those things. So as you can see, if I go down, so everything, right, you can see everything is assigned an address, and whatever is the description of it, everything is present in this system.htf file, right? So this is the default page that will be open once you launch the SDK. And so far we have done the hardware implementation. We have exported the hardware and we have launched the SDK. So that was all about the part one. For part two and three, we will do in the next part of this video. Thank you very much.